Welcome to section 3.4, day 1. Derivatives of exponential functions. And exponential functions have the form y equals a times b to the x power. So today we're going to differentiate exponential functions. So the derivatives of a to the x power. So the derivative of a to the x, some base raised to the x power, where your variable is in the exponent, is a to the x times the natural log of a times the derivative of that exponent, whatever that would be, so dy dx. It may be necessary when we do this to use the chain rule. Using our rule, y prime is a to the x power ln of a times dy dx. So we're going to use this rule to take the derivative of 6 to the x power. So we have y prime is what we start with, 6 to the x power. Then we take the natural log of the base, and the base in this case is 6. And we take the derivative of x. The derivative of x is just 1. So we have y prime is 6 to the x ln 6. This is my derivative. For the second one, we have our y prime. Our base is, we have y equals 9 to the cotangent of x, and our base is 9. Cotangent of x is our exponent. So our first part is we just take what we start with and write it down again. Then we take the natural log of the base, which is 9. And then we take the derivative of cotangent x, which is negative cosecant squared x. Make sure you put that in parentheses. A little hard to see the rest of it, but it's there, negative cosecant squared x. And then we have y prime. We're going to bring this out front. So we have negative cosecant squared x, 9 cotangent x, ln 9. This is my answer, negative cosecant squared x times 9 cotangent x ln 9. So we take our base to the power, we write that down again, we take the natural log of the base times the derivative of the exponent. That is how we find the derivative of an exponential function. So now we move on to the derivative of e to the x. So we take the derivative of e to the x, we follow the same rule. We take the derivative of a to the x is, again, the base to the exponent times the natural log of the base times the derivative of the exponent. But e to the x is sort of nice because the derivative of e to the x is just e to the x. And it may be necessary again to use a chain rule. If I have a function y equals e to the x, what happens if we take this rule is we would have y prime is, again, e to the x, the natural log of e times the derivative of x, which is 1. Well, the natural log of e, these are inverses of each other. The natural log and e are inverses, so it just becomes 1. And so y prime just becomes e to the x. So the derivative of e to the x is just e to the x because of this algebraic rules. All right, so now we say what is the derivative of y equals 15 e to the x power? Well, in this case, again, it's just y prime. The e is what's being raised to the x power, not the 15, so we just have 15 coming along for the ride. And the derivative of e to the x is just e to the x. For the second one, the 7 again is just coming along for the ride. What's different with this one is we do have to worry about our exponent. So we have e to the negative x, which is still e to the negative x. The derivative of negative x is negative 1. So this is negative 7 e to the negative x. So we have to take the derivative of the exponent. We just have e to the x. The derivative of x is just 1, which I showed on the last slide. But here we have the derivative of negative x, which is negative 1. We have to account for that. So y prime, we have our exponent is 4/5 x. I'll put in the same way we've been doing this. we have e to the 4/5 x. The derivative of 4/5 x is 4/5. So then we get 4/5 e to the 4/5 x. And there's my derivative. So now we're getting a little bit more complicated. We have y equals 2x e to the 3rd power plus e to the negative x. Be careful with this. E is just raised to the 3rd power, so e to the 3rd power is just a number. It is nothing else. So it'd be like 2e to the 3rd times x. So in this case, all we're actually taking the derivative of is where the variable is. For this one, we just take the first part, we take the normal derivative, 2x e to the 3rd. The derivative of x is 1, and we get 2e to the 3rd. And then we have e to the negative x. We've done one recently above. And you can see that if we take the derivative of negative x, we get negative 1. So we have negative e to the negative x. This becomes negative 2e. And because we have e as the base and we have 3 minus x, 3 and negative x as our exponents, we can combine them if we want to. We could take it negative 2e to the 3rd, e to the negative x, or we can combine these into negative 2e to the 3 minus x. Remember, when you're multiplying bases together, you add the exponents, and 3 plus a negative x is 3 minus x. Now we have a more complicated one. We have y equals e to the x squared. Same idea applies. Y prime. E to the x squared, we still have e to the x squared. But we need to take the derivative of x squared, and the derivative of x squared is 2x. So y prime is 2x e to the x squared. And that is my derivative. All right, so that's our derivatives of an exponential function with the base of e. Now we move on. It says find an equation for a line that is tangent to the graph y equals 2 e to the x, and this one goes to the origin. So we know one of the points we go through is 0, 0, because the tangent line goes to the origin. So point 1 is 0, 0. This does not say that we want to find the point of tangency at the point 0, 0. This is saying the tangent line goes through 0, 0. Well, if it goes through 0, 0, and this is my function, the place where it's on our graph of y equals 2 e to the x, the point we're looking for is when we plug in some x value. When we plug in some x value, we get 2 e to the x back. This is my point 2. So we know the equation of this line is going to go through these 2 points. All right. So now we're going to look at how can we figure out our slope. We have 2 points, so now we need a slope. To find the slope, we need to take the derivative. So y prime of 2e to the x is 2e to the x. We take the exponent, we have e to the x, so we write it down again. The derivative of x is 1, so our derivative is 2e to the x. Well, we know our slope is this, 2e to the x. We also know we have 2 points, so let's use our slope formula. Set our slope equal to our points in the slope formula. So 2e to the x has to equal our y values over our x values using our slope formula. So 2e to the x equals 2e to the x over x. Well, if you sort of think about this, we do the mathematics. How could we have 2e to the x equal 2e to the x over x? Well, the only way this works is if x is 1. And you can solve it algebraically if you want, but you can see this sometimes. In this case, x has to be 1. So at x equals 1, our slope is 2e to the x. So now we know we're looking for the point of tangency when x equals 1. That's the only way that slope formula works, is if x is 1. So we're going to plug 1 into our function and get our y value. So now we have y equals 2e to the 1, which is just 2e. So we have our point of tangency is 1 2e. We have a point. We have a slope, but this slope still is in a function form. We know our x value at our point of tangency is 1, so we can actually find our value for y prime, our slope. So our actual slope would be 2e to the first power, and when you do this, you get our slope, our y prime is 2e. So we have our slope, our m is 2e. We have a point, so we can use either point. We can use 0, 0, or 1 and 2e to write the equation of our line. Either one doesn't matter. We have our slope is 2e, so I'll use 2e. I'll use the second point, 1, 2e. So we have 2e plus the slope, 2e, x minus 1. And then when we do this, and we could simplify this, we can leave it like this too, but we can simplify this one nicely. Y equals 2e plus 2ex minus 2e. The 2e's cancel out, and we get y equals 2ex. And that is the equation of our tangent line. That is all for section 3.4, day 1. So the derivative of e to the x is e to the x. If we have a base that's a number, like a to the x, you take a to the x times the natural log of the base times the derivative of the exponent. Again, the exponent would have your variable in it. It may be necessary to use a chain rule when we do these. Make sure you're showing your work on your homework. Thank you for watching, and have a nice day.